So last time we looked at skewness metric, which is more about understanding whether a distribution is symmetric or not symmetric, whether it's skewed towards right or left. Kurtosis is a different metric. It is more about understanding whether a distribution is light-tailed or heavy-tailed. And that depends on what kind of deviation that may exist or is allowed to exist away from the central tendency. And this is why when we would like to understand kurtosis, we would like to know how, to what extent, or what is the magnitude or the difference between each response variable value from its central tendency, which is in this case mean. So we'll quickly start with the data frame object, and we'll work with our diabetes data set with the response variable y, and I will calculate the difference between each response variable, each value of the response variable from its mean, and then scale with the standard deviation. So this scale difference allows us to understand what is the extent of deviation that exists in each response value, scaled using the standard deviation. So the scale is relative with respect to the standard deviation. So we'll quickly do the data frame, which is named as df code. So first column is y, and the second column is the normalized variable. And we'll have to quickly rename the columns. So let's do that. And then let's examine the first few values. Once I do that, I'll have to define a custom function, because to calculate the kurtosis moment, I would have to further transform the scaled value by raising to the power of 4 and then subtracting 3 from it. So to do that easily, I'll quickly define a custom function called kurd function, and this function will take each normalized observation value, raise it to the power of 4, and then subtract 3 from it. And since I'll have to do that for each normalized value observation, we'll have to use the lapply function that will do it for each of the scaled value that we computed before. And so that gives us the final kurtosis transformation. We'll have to do a quick numeric adjustment so that I can apply more arithmetic function on it. And then I will create a variable called k moment, and then calculate the mean of this transformed variable by summing up each value and then dividing it by the length. And even if I do a quick summary of this, that is the transformed variable, I could find out the mean, which is same as the kurtosis moment. So in this case, the value is 0.8962. A good way to visualize this is through the standard histogram functions, and then we can also compare this with the normal function. So the way this transformed variable looks like, if I do a histogram, you can see that the values are clamped towards the right, right? So these values are restricted, they're clamped down towards the right, and they're high towards the left. Now, if we compare this with a normal distribution, which is done through R norm, and when we plot the histogram, you can see a bell curve. So that's how quickly a difference between a distribution which has a different tendency to allow deviation from the central tendency can be observed and compared with respect to the normal distribution. Another way to look at this is through the plot function. So I'll just do the plot command, and then you can see the same histogram that we saw, which was clamped towards the right. You can see that in the plot density as well. And similarly, I could do this plot for the normal function, and you can see a big curve. So that's a quick way to visualize the kurtosis.